All right, so today we have Luke Bartels from Oak Ridge, and he will talk about the large-scale quantum chemistry applications with sample-based quantum diagonalization. So I'll hand it off to you, Luke.
All right, thanks, Amir. So yeah, I wanted to, so thanks for the invitation today. I just, in light of the discussions we've been having in the openQSE, I wanted to talk about two kind of recent publications that have come across my desk that are highlighting what can be done with near-term quantum chemistry or near-term quantum computers looking at quantum chemistry. So these are two papers. Let's see. Yeah, these are two papers that are coming out of the work from the Cleveland Clinic, MSU, IBM, and Riken. So the first one that we'll look at is called Molecular Quantum Computations on a Protein, and that's looking at sort of two conformations of a protein. And then there's a follow-up paper that is on the archive right now that is kind of a scaled up version of that, better optimized for use with HPC. So let's start with the first one. So the idea here generally is, hopefully most everyone knows, is that simulating the many-body electronic structure of molecules and materials has long been promised as one of the most promising applications of quantum computing, going all the way back to Feynman. So in the work that we're looking at here, this is a version of what's called quantum selected configuration interaction and sample-based quantum diagonalization. So previous studies looking at this, led by IBM, have scaled this up to about 36 molecular orbital examples. And the idea here is that instead of in typical VQE, where you would use your quantum processor to directly make measurements of your Hamiltonian expectation values, here instead you're using the quantum device to prepare states and then sample from a distribution. And then you're using that distribution to build a reduced dimensionality Hamiltonian, which is then diagonalized with classical hardware. So that's been done on 36 molecular orbitals, but to take this up to something of biomolecular scale, and this is a problem we have in classical quantum chemistry as well as quantum chemistry. Yeah, these sizes just become intractable for what's available with near-term hardware. So to scale these up, we want to look at what are called embedding or fragment-based techniques. And the general idea there is you take a chemical system, you intelligently break it down into a bunch of smaller subproblems of reduced dimensionality, and then you have a clever way of stitching those back together to reproduce your full system energetics or other properties. So in the specific paper we're looking at, they'll be using what's called wave function-based embedding methods, or EWF, which is a non-iterative scheme that uses atomic-based fragments. So in the systems we'll look at, there will be, I think in the first one is 303 atom protein, and then it goes up to 12,000 atom proteins. So each of those systems is going to be treated, or each of the atoms in those molecules will be treated as an individual fragment under their embedding scheme, and then it'll be processed with this quantum selected CI, which will then go through a sample-based diagonalization routine to get properties, and then stitch back together to get full system properties. So in the first work, we're going to look at two conformers of this TRP cage mini protein, which I said is about 300 atoms. So when we fragment that, that'll span system sizes of 6 to 33 MOs. So maybe for those who aren't chemists here, to get kind of an idea of the dimensionality we're talking about. Normally in chemistry, when we map it onto a quantum computer, we'll use what's called the Jordan-Wigner mapping, which will, each MO will get mapped onto 2 qubits. So you can think of these as then roughly 12 to 66 qubit problems. There will be a few extra in this case due to the mapping of the hardware that these will be mapped on, but that should give you a rough idea of the problem sizes that are being dealt with here. So just kind of going through a general workflow again, we'll first generate clusters with this embedded wave function method on classical hardware. We'll generate fragment properties with this sample-based quantum diagonalization, which is a hybrid quantum classical approach, and then reconstruct total energies from the fragments, which will be purely classical again. So here's kind of a general overview of the workflow, and we'll go into each of these areas in a little more depth as well. But here we have one conformer or sort of geometric configuration of our protein. Here's a second one folded, and what we're looking at from a chemist perspective is the thermodynamics of this. So we want to know what is the energy difference between these two structures. So to go through this, we have methods that are purely classical in red, and then methods that lean on our quantum processor are going to be in blue here. So what we see is that we'll do some preparation to the fragmentation. Then we'll take each of these fragments and we'll perform this sample-based quantum diagonalization on them, plus some classical references to get out some local properties. Those local properties will then be used to reconstruct the total energy here. And we'll get an energy difference by just comparing the difference between those two energies. So to start, let's start by talking about this embedded wave function method, or EWF. So it's inspired by another method from classical electronic structure theory known as density matrix embedding theory, where you separate your system into fragments that are surrounded by a bath of orbitals. So kind of walking through this workflow here, you'll start with a very basic description of your problem, your geometry. You'll solve a full system mean field calculation. In our case, that's Hartree-Fock. And then you'll do what's called a Schmidt decomposition, and that will localize the orbitals to atomic fragments. And the idea here is that you want your orbital sets localized, sort of tagged to a single atom in order to do this fragmentation, because you'll have a set of MOs associated with each atom. So from there, what the authors do is they, to go beyond sort of the coarse level DMET, they use a correlated wave function theory known as MP2 to define an interacting set of bath orbitals. So what that does is that introduces some notion of electronic correlation at this sort of low level fragment approach. And what that does is it allows for more accuracy to be captured by this atomic fragment approach, which is otherwise a pretty extreme approach in a lot of chemistry methods. There will be some user-defined bath threshold here that determines which set of natural orbitals from this MP2 diagonalization that you're keeping. And then those will be combined with your fragment and a bath to give a set of embedded wave function clusters or embedded wave function fragments, which will be written out to these fragment.h5 files. So you'll have one of those for each atom. So going from there, you'll then take those, for each of those fragments, you'll perform either a classical exact diagonalization if it's small enough, or a sample-based quantum diagonalization for the larger samples. So that's going to proceed as a hybrid quantum classical solver. So this is really the only spot in this algorithm where we're leaning on the quantum hardware. And again, that's as a quantum sampler. So we're trying to sample different configurations in the wave function itself. So we'll use, like I said, the quantum hardware to prepare and sample candidate electronic configurations. That's done using an ansatz. So the ansatz that is being prepared here is this local unitary cluster Jastrow ansatz, which you can seed with a relatively cheap couple cluster calculation on the fragment itself. So what that's going to do is prevent a lot of costly optimization of parameters on the quantum hardware itself. From there, classical HPC is used to perform error mitigation and subspace diagonalization. So you'll map your system or map your problem onto the quantum hardware. You'll optimize your circuits, transpile it down to gate level instructions for the quantum device, and then perform a sampling over 1 million shots per fragment. And then from there, you need to do a lot of cleanup because we're obviously in the noisy intermediate scale quantum error. So what's going to happen is you'll perform this error mitigation routine called configuration recovery, and then diagonalize in the subspace of the cleaned up configurations that you generate. And there's an extension here called this extended sample-based quantum diagonalization. And what's going on in that algorithm is, in addition to the sampled states after configuration recovery, you, in order to better give coverage over states that give support to your ground state, you'll take the states you get from the quantum sampler plus cleanup, and then look at, in addition to those, single excitations around the dominant configurations coming from pre-diagonalization of those states. So here's some more discussion of the kind of starting of our algorithm, where again, we'll perform a full system Hartree-Fock calculation. They used the GPU for PySCF package with a minimal basis plus density fitting to make this, rather large even mean field calculation feasible. So this was performed on a GPU accelerator, and it took about 4 minutes per conformer. Then to go from this mean field full system calculation to the embedded wave function cluster formation. Again, we're doing an interacting bath expansion with MP2 natural orbitals. This was done over on a 4-core CPU, and it takes about 30 minutes of wall time for the full system calculation here, and then those individual fragments are written out. So if we look at a sampling of those fragments for the different conformers, we have the folded conformation in blue, the unfolded in green, and we see that when we break the system down into these atomic fragments, we have about 150 fragments that are in the 6 to 14 MO range, about another 150 that are in the 15 to 33 MO range. So this vertical dashed line here is going to separate the states on the left, which will be solved with exact diagonalization because the Hilbert space of those problems is small enough to diagonalize exactly, kind of trivially. Versus on the right side of this dividing line, these are the fragments which will be treated with the sample-based diagonalization approach. So like I said, for fragments that are greater than 15 orbitals, that should be fragments less than 15 orbitals are solved with classical diagonalization. For the 15 to 33 orbital fragments, they'll be solved using this extended SQD with a classical reference. The sampling is using this local unitary cluster Jastrow ansatz with a single layer, and it's 1 million shots per fragment, which will be executed on IBM's Heron R2 QPUs, which are a heavy hex layout. So here we have the layout of the spin orbitals. So we have the alpha orbitals in red, the spin down or beta electrons in blue, and we have some ancilla qubits that facilitate the interactions between your alpha and your beta spins here. So this is the layout. This is will then be hit with a single layer of this local unitary cluster Jastrow ansatz, and then measured in the computational basis to extract configurations. So going beyond that, now that you have all of your measured samples, you'll want to do what's called configuration recovery and subspace diagonalization. So here, the process you can kind of see here will will take all of your bit strings which do not have the proper Hamming weight, which in this case corresponds to the proper number of electrons for the system. We'll perform a diagonalization and will, based on the occupation numbers of your correct, excuse me. So based on the occupation numbers of the correct samples, you'll use those to perform configuration recovery to correct probabilistically and try to determine where these errors occurred. It's the most computationally intensive aspect of this algorithm, and it's both asynchronous and quite parallelizable. So for the smaller of the quantumly treated fragments, these were performed on the Michigan State University HPC cluster over 80 to 100 nodes. And for the larger systems, these were treated on the Cleveland Clinic Foundation's HPC resources with large memory nodes. So these are 3 terabytes of RAM and 96 CPUs, or 6 terabytes of RAM and 112 CPUs. But in general, the idea here, after your configuration recovery, is you will recover a lowest energy batch of configurations, which will then be extended by considering single excitations coming off of them, augmenting the subspace, and then doing your final diagonalization to extract your energy and your 2 RDMs, which will be used to construct then the full system properties and energy. So if we want to look at how our Hilbert space is reduced with SQD and in this extended SQD, so on our y-axis here, we have the dimension and log scale. On the x-axis is the number of molecular orbitals considered in each of the fragments. And what we see here is a several orders of magnitude reduction. Even for our smallest fragments, there's about a 1 order of magnitude reduction versus in our largest cases, we have an enormous reduction occurring with this sample-based diagonalization technique, which is good because this diagonalization is being performed classically. So yeah, these Hilbert space sizes would not be feasible beyond about 22 molecular orbitals otherwise. Is there a hand up?
Quick question. What is the origin of this reduction? Is it because you are doing part of your LHCJ propagation quantumly and then compressing to some subspace, spitting out a Hamiltonian and then diagonalizing on a classical computer?
Yes, exactly. So the source of this reduction is coming from the idea that, so you're using your LUCJ ansatz to preferentially sample the important configurations in your overall fragment wave function. And then, this is, the black bars here kind of are the full configuration space versus the blue and red are the kind of down selected sampled configuration or number of configurations, which, exactly.
So, and how do we know that this reduction is accurate in the sense that do they both give you the same energy accuracy, or like how do you know?
So you don't necessarily know a priori, or for a general system. The idea is that you're somewhat leaning on the idea that chemistry Hamiltonians have structure to them, that there is a hierarchy, especially around your mean field solution, where you have some idea that you should have these high weight determinants that are contributing, and that in principle a quantum device should be, if properly initialized, should be able to sample those efficiently.
Right.
But
Yeah.
they do, yeah, for purely diagonal or for systems that are exactly diagonalizable, they have tested this and demonstrated its accuracy.
Right. So perhaps so I agree with the fact that chemistry Hamiltonians, just like condensed matter Hamiltonians, have special structures. They have locality, they have symmetries, so on and so forth. But the curve seems to be saying, it's like there's something growing exponentially versus something which is more constant, right?
Right.
This is non-trivial, and the only way for this to work in practice would be your QPU. You can scale the quantum circuit depth on those to kind of trade off this thing. But right now we're in NISQ QPUs, and I'm pretty sure you can't do that. So I'm a little bit surprised about this flatlining.
Right. Well, so that is one way to think about it. I think another way to think about it, sort of borrowing off the condensed matter idea, is that there's some locality of electron correlations in these systems, and then that locality would not grow, or would lead to those correlations not growing exponentially, but be, softer scaling.
Right. But maybe I rephrase my question. So I agree with you, but let me rephrase it, because
Sure.
there still has to be some scaling, in the sense that for the red and the blue curves, it's presumably either the quantum circuit depth or the SQD runtime for your classical processor should still be scaling up as you go to larger molecular orbitals.
Sure.
Right. Is that true? Or otherwise, I would be very surprised with this result.
I would tend to agree with you. Yes, that it should be scaling up. So what might be happening here is might be hitting sort of the extent of what you can sample with a finite number of shots and a finite circuit depth.
Right. In general, my feeling is that these things are trading off the pure classical computation, splitting it, and then a lot of the heavy processing is being done by the classical supercomputers, right? So even in a lot of simpler, let's say, molecular orbital scenarios like iron sulfur cluster papers and so on, it seems that you start from a Hartree-Fock state and you do your LUCJ circuit. It may actually make your energies worse than Hartree-Fock, and then you have to do a lot of spin restoration and post-processing to actually bring it better, right? So we have to be, all I'm saying is we have to be careful about these trade-offs.
Right, exactly.
Okay. Awesome. Thank you.
Cool. So going on from there, here they highlight the memory requirements to perform these SQD and extended SQD experiments. And these are over, the entire set of fragments in that given size. But what they observed was by performing this batching procedure, they could get this overall gain versus trying to perform the entire SQD in one shot. And this batching is then used to inform this extended SQD. And similarly, you see that the average runtime is quite heavy for these systems, where this dashed line here is roughly 1 day of compute time, or compute wall time. So while the but again, if we look at the distribution of fragments, this might initially shock you because the largest molecular orbital cases are taking the least amount of time. But this is again over all of the different fragments, and there are more fragments in this 25 to 30 molecular orbital range than there are in this 31 to 33 range. So that's why performing all of these takes more time in that range. So some quick results and conclusions. So the total energy for the whole protein system is reconstructed from these 1 and 2 RDMs from the fragments that are then projected and symmetrized into the full system basis. This gives us then an n representable, which means that it can correspond to a realistic wave function, global expectation values. This represented, at the time, the largest embedded CI calculation to date, and was the first example of a biological scale problem treated with quantum sampling. And kind of going back to the question about the accuracy of this SQD, the authors provided two classical benchmarks. So this is an embedded wave function MP2, an embedded wave function couple cluster with single and double excitations. And what they found was that if we look at the energy difference between the folded and unfolded configurations here, the quantum approach lies somewhere in between these two classical approaches, which would suggest that the SQD isn't too far off what we would expect reality to be. So moving on to the second paper, which is then.
Quick question, Luke.
Yes.
Sorry. In the previous table, can you remind me what the Hartree-Fock energy without SQD would be? If you happen to know.
I do not know off the top of my head.
Okay, great. No worries, because again, I've found that part without SQD can be quite worse. And yeah, it'd be good to keep those separate, where just pure Hartree-Fock, Hartree-Fock plus LUCJ, or one of these, one of your favorite ansatz, and then the one which is with SQD, so that we have a good sense of how much of the heavy lifting is coming from SQD versus the QPU. Yeah.
Sure.
Thank you.
Was there another question in there?
Yeah, this is here. If I can ask questions about resource demand and the trade-off. So if I understood correctly, in the extended or the other SQD, you were trading off, in here, right? Memory for time execution. Is that, never mind the implications on the accuracy of the result. Did I read it correctly, or am I on the wrong track?
That is my understanding as well. So they were trading off memory, where these red extended SQD batch, these red bars here represent a more accurate approach doing this extended SQD, but at the cost of higher total memory usage than these SQD RAM batches. So these light blue, the light blue bars represent the sort of single shot overhead
I see.
for an SQD batch, whereas the red bars are not batched.
Okay, and so this, the next slide I think has like the time runtime total, right? And so I think this one, that's the trade-off. I was like, okay. And can you explain to me what is the the million shots per fragment, or how big is a circuit? And million shots is a lot of shots depending on how big the circuit is and how fast the QPU clock is.
Sure. So I believe I want to say the circuit runtime, it's about, it's about 27 nanoseconds per 2 qubit gate. I think it's roughly 250-ish gate depth. So I think.
Okay, so it's tractable, given the modality of the hardware used and given the sort of fairly small circuits, right? You can afford the million shots, so to speak, right? What's specific about, what is significant about a million shots? Is it that you want to be super sure about the results fidelity, or is it a artifact of the algorithm? Is it an artifact of the NISC or the fidelity and the noisiness of the system?
My reckoning would be that the relevance of the 100 shots is trying to get good coverage or get a reasonable diversity of configurations to see the configuration recovery.
Okay.
algorithm.
Right. Yeah.
But I think that is also a limitation of NISC. You know, in principle, if you could do more, it would be better to have more.
Right. Okay. Yeah. Thank you for now. I don't want to hold the second half.
All right. So yeah, the second half of this talk will be on another paper where the original authors, in addition to Riken supercomputing, are now scaling this up to something roughly 40 times the size. So instead of just looking at a single protein, they will now be looking at two protein ligand binding energies, which are important properties for drug discovery applications. So this will be related to the strength of, if you have a protein with some active site, you have a ligand which can represent a drug molecule, how tightly does that bind into a given pocket? So like I said, this will be two complexes which are roughly 11,500 and 12,500 atoms. This will be explored using two 156 qubit quantum computers, one in Cleveland and one in Japan. And to do the classical post-processing, instead of using local resources, it's now getting stepped up to leadership computing at Riken, Fugaku, and Miyabi-G, the latter of which is a GPU cluster. So some improvements on what we've just seen is this will now take the quantum embedding method down to sublinear scaling. They'll introduce a new sample-based quantum diagonalization approach to increase the accuracy over what was done previously with the extended SQD. They introduce a selected basis diagonalization, GPU accelerated diagonalization subroutine, and look at, like I said, systems that are roughly 40 times larger than the previous state of the art that we just talked about. So here's another workview overflow. Very similar starting case where we have, if you want to measure now a binding energy, you need the bound system, the unbound system, and the ligand. So taking the difference between this and these two should approximate your binding energy with, yeah, some approximation there that we'll get to. So this will again take a full system mean field calculation, will be processed through this modified fragmenting algorithm, then given off to a quantum hardware to perform a quantum sampling, and then this configuration recovery and subspace diagonalization, and then again reconstructed from those fragment calculations to give a full energy. Yeah, and they'll provide some classical references as well. So as we saw before, in order to do this embedded wave function method, you first need a full system mean field calculation and orbital localization at roughly a scaling of the number of orbitals cubed. Then you need to do an atomic orbital to molecular orbital transformation, which costs, well, if you're doing it quickly, the number of orbitals scales with the number of orbitals to the fourth power.
The value operator. Yep, one for each A.
Yep. And then the full system MP2 calculation to get the correlated bath orbitals scales as roughly the number of orbitals to the fifth. So to improve on this and this work, they still need to do the full system Hartree-Fock, but instead of performing a full system MP2 calculation, the orbitals considered for the perturbation theory excitations are now only those within a cutoff radius of each atomic fragment, and they choose a 7 angstrom cutoff for this. And similarly, instead of reconstructing the electron repulsion orbitals in the full space, they restrict the construction of these electron repulsion orbitals only out to about 10 angstroms from any given center. So they're working with explicitly localized quantities instead of the full system quantities in order to scale. Oh, Go ahead. Is there a question?
Luke, do you have an understanding of how good these fragment molecular orbital methods are here? Because generally they seem to have much better scaling with the number of orbitals, right? Supposedly order n.
Right. So I do not have a good, I don't have a reasonable, I don't have a good approximation for how good this particular embedding method is.
Right.
But but in general, most of these embedding approaches, you will have to do some level of mean field calculation. So you'll kind of bottom out at this cubic cost, and you can change the prefactor on that a lot with density fitting, but that will to some degree dictate, at least for chemistry, the best you can do there. But then the but then the improvement here then is again, making an approximation about the locality of correlation in the system to impose these cutoffs for constructing the fragment properties.
I guess my statement was it would be, given that we are in this near term where everything on the quantum side is very expensive, maybe FMO methods which promise order n scaling linear in the number of orbitals would be the kind of thing to investigate. And
we are actively investigating that as well.
Okay, awesome. Okay.
Yep.
Yeah. Thanks.
So now improving upon the extended SQD, they're now doing a method called trim SQD, which introduces trimming of determinants over the previous extended SQD method to achieve higher accuracies, and that's done with this two-level diagonalization. So within this configuration recovery loop, you'll then batch sample configurations for subspace diagonalization and only keep those with a weight above a certain threshold K1. Then there's a second level of filtering of configurations here to keep those with configuration weights above K2. And the configuration set, instead of being extended with just single excitations as it was in this extended SQD, is now extended with all configurations that are 1 and 2 particle excitations, so singles and doubles excitations away from the original set in this subspace extension. And then the final diagonalization is again performed over this entire extended subspace to output energies and 2 RDMs. And then this is accelerated using this SBD code, which is an in-house diagonalization code that the authors developed to accelerate the parallel execution using a distributed memory design to store the configurations and GPU acceleration. So there are 2 test systems they looked at. One is this trypsin benzamide, which is a serine protease enzyme and its inhibitor. You can kind of see it in there. So this will be a 12,635 atoms, which corresponds to then 31,000 and change molecular orbitals. The other system they look at is this T4 lysozyme with N-butylbenzene, which is an artificial protein and a ligand known to have high nonpolar binding affinity. This will be 11,600 atoms and almost 29,000 MOs. And there's a picture of it there. So if we look at the fragmentation of this, these are looking now only at the fragments that will be treated by the QPU. Everything smaller than 12 MOs is diagonalized classically. So for the first system, we have roughly 42 or 4,300 individual fragments to be calculated in the 13 to 26 MO space, and then another 550 in the 27 to 45 MO space. These smaller fragments will be, we'll collect 100 samples. The the first system was only using the IBM Cleveland processor, while the second system uses both IBM Kobe and IBM Cleveland. The per fragment QPU time is roughly 30 seconds for these smaller fragments and 142 seconds for the larger fragments. So all told, there's about 106 total hours of QPU time required to do the sampling for these systems. So to do the quantum resources then, as I said, are two of these 156 qubit Heron R2 quantum processing units, IBM Cleveland and IBM Kobe, 106 hours total runtime to measure 92,000 total quantum circuits, about 1,000 of which were the larger sizes, which get mapped to between 58 and 94 qubits. The largest circuits, were 94 qubits, about 250 2-qubit gate depth with an execution time of 17 microseconds, which is well under the roughly 150 to 200 T1 and T2 microsecond T1 and T2 times for these quantum processors. And in total, about 1.3 billion shots were collected. So then to process these, the classical resources were Fugaku, which is 160,000 nodes, using Fujitsu A4 FX processor. So these were each done with 48 compute cores and a 32 gig high bandwidth memory. For the GPU resources, this was the Miyabi G cluster, which is a GPU accelerated 1120 NVIDIA GH200 Grace Hopper superchip, which is a 72 core NVIDIA Grace CPU with a NVIDIA Hopper H100 GPU. So for the looking at the rough timings, again, we have about 106 hours of compute time on our quantum resources. And then the sampling based diagonalization configuration recovery was 396,000 hours on Fugaku for Tripson, 308,000 for the T4. And on Miyabi G, that was 4281 and 3554, which means that if we look at node usage, our quantum devices are obviously single node, but in the largest cases for IBM Cleveland, they were using 94 qubits, which is roughly 60% of the qubits available. For IBM Kobe, that was roughly 40 qubits, so roughly 25% of the available qubit resources on that QPU. If we look at the supercomputing, then they're using at peak 97 or 95.7% of Fugaku and 98.6% of Miyabi G. So the total runtime on Fugaku was about 4.5 hours, 2.5 of which was 2.3 of which was work-bound runtime, and 9.5 hours on Miyabi G, about 3.8 of which was work-bound runtime. For Tripson, this calculation sat in the queue quite a while on Fugaku, but it was only about 1.9, just about 2 hours of work-bound runtime on Fugaku, and about 3 hours of work-bound runtime on Miyabi G. And at 64 node parallelization, the selected basis diagonalization routine was able to achieve a parallel efficiency of 72.5%, which is quite good scaling for this diagonalization routine. So if we now look at the results, we can compare both the embedded wave function couple cluster to this embedded wave function trim SQD. So this will be the classical reference. We see rough agreement between the overall binding energies, but you might notice that in both cases, the binding energies are positive, which means that these systems are not bound at this level of theory. There's a couple of things to equate to that. So that could be attributable to the minimal basis size used. These aren't counterpoise corrected. And this could at some level be an artifact of the level of embedding used, but there are a lot of sources of error to kind of look at here to explain why the binding itself is positive for these systems, but the rough agreement between the classical and the quantum resource should suggest that the quantum isn't doing anything particularly wrong in this case. If we look at a couple of selected fragments, what we see here is our trim SQD reference in orange, and that is able to roughly achieve the accuracy of DMRG, which is the reference for these calculations. And these are single fragment calculations. So given enough time to compute, what we see is that the trim SQD is able to significantly improve upon the accuracy of what was, for this, the state of the art in blue, this extended SQD, and again is approaching the classical DMRG reference. So just some quick conclusions here. So by exploiting localization, the authors were able to scale their embedded wave function method to over 12,000 atoms. By using a two-level filtering, they're able to increase the accuracy over their extended SQD. With 92,000 circuits and 1.3 billion measurements, this stands as the most quantum resource intensive quantum chemistry study to date. Limitations on the basis set and the embedding do not predict binding, but they're in good agreement with classical benchmarks. And this GPU-enabled selected basis diagonalization routine enables massive parallelization on leadership computing. And in both of these studies, the quantum and classical resources are asynchronous, which it doesn't exactly testify to the tight coupling of the quantum and classical resources that we're exploring in this working group, but it does kind of stand as what is now a kind of a flag in the, or a line in the sand result for quantum chemistry. And with that, I'll end and take any more questions that we have.
I got a quick question.
Go ahead, Amir.
So for that, again, I'm not a chemist, but for the 12,000 atoms, like to actually have something that is useful, how many atoms are you supposed to handle?
12,000 should definitely be useful. So just to kind of look at what they're working with here. Yeah, I guess if you're not a chemist, you're probably not a biochemist. But what we're talking about here are kind of small to medium-sized proteins, which are represented by these kind of ribbon structures here. And these are benchmark cases that that are used in classical electronic structure theory to study binding in drug protein binding interactions. So in principle, if you could nail this problem, this would be something very useful. For general chemistry cases, it's been speculated that maybe 100 to 200 physical qubits, you could start to do kind of interesting things. So that's maybe twice the size of what they were looking at here for individual fragments.
Sorry, physical or logical did you mean? Sorry.
Or sorry. Well, in this case, physical is logical. But yeah, there's been speculation that, at somewhere between the 100 to 200 logical qubit scale is where you would start to see sort of transformative results in chemistry that are hard to produce with classical results.
So maybe I missed this. The classical portion of the classical counterpart of this algorithm or
Mhm.
the counterpart of the hybrid one, can it handle the same number of atoms at the same about time scale, or does it take longer? Does it take shorter? What's the difference?
It takes significantly shorter.
The classical one.
The classical does. Yeah. Because it's, well, yeah, with the same embedding scheme, it takes significantly shorter. Because you're, again, solving a small problem that, yeah, once you fragmented it, you've made it a size that the leading classical methods can treat well. So that's, for example, why kind of at the end here, they're using DMRG as a reference. So at the roughly 35 to 45 orbital scale, yeah, that's something that classical computing can nail. But the promise is that, yeah, if you could maybe go to twice this size, you would start to be in an area where you start to see that breakdown of classical compute for these strongly correlated problems. Because I think DMRG has scaled up to roughly 100 electron and 100 orbital problems.
There are a couple more questions there. Michael, you want to go ahead?
Hi, yeah. My question's about this slide and is sort of along the lines of what Amir was asking. So we have here a comparison of a classical method and then the hybrid quantum classical method.
Mhm.
The CCSD method, is that less accurate than the quantum one? Is it the case that the work here is demonstrating something that's more accurate than any known classical technique for this problem?
So it's not better than any known classical technique. So yeah, in this case, the DMRG here, so in these fragment calculations in red, that would probably be among the better classical results. Yeah, at this scale, that's probably as good as you're going to do classically for these system sizes.
But that's not, that would be kind of like if they did their whole way of dividing everything up to fragments and then they used DMRG instead of their other method.
Right.
But they didn't do that, right? They're comparing against this CCSD, which is presumably a totally different method.
Right. So that's going to be this black curve here. And that's with the same fragmentation. So that's CCSD, yeah, using the same fragment approach that's being used for this for the quantum approach.
I see. So from those graphs, it looks like it would be more accurate.
Yes.
If I'm understanding correctly, than the CCSD one. But if they did the experiment with DMRG instead, which we think they could have done, then it wouldn't have been.
Correct.
Okay. Thanks.
Yep. But neither, yeah. So, and maybe this was motivated earlier. The reason they are performing these sort of localized MP2 approaches and localized electron integral transformations to do the embedding in the first place is because MP2, which is one of the cheaper correlated wave function methods you can perform, won't scale to the full size of the system. That has an end of the fifth scaling, and that breaks down at this scale. So they would not have been able to perform an MP2 calculation at the full system size, much less a couple cluster calculation.
Thanks.
Ermal, I think you're next.
Yeah, I had a follow-up actually on this. I'm a little bit puzzled by your comment about the 100 to 200 logical qubit gates. What's the error rate you have in mind there?
Yeah, I didn't have an exact error rate in mind. I was assuming perfect qubits.
Okay,
Or,
because I'm thinking for this DMRG, do you know the bond dimension?
I don't know the bond dimension for these DMRG calculations. No.
Because that would be one way to compare. The size of the DMRG can tell you the depth of the circuit to build that DMRG.
Mhm.
And then you have to convert it into the T gates required, right? So it would give you a bound on how many T gates you need just to do the DMRG on a computer.
Right.
Right. So usually they end up being very deep. So
Yeah.
maybe not early fault tolerant.
No, certainly not early fault tolerant.
Yeah. Okay. Thank you.
Just to make sure we're on the same page, there's no claim of quantum advantage here, right?
Correct. Yeah, they're not claiming quantum advantage here. Yeah, this is a demonstration of something you can do with quantum that has, yeah, it'd be hard to say utility here because they're spending, I guess, what, 100 hours is 4 days and change to do the sampling here versus, these couple cluster calculations in that active space should fly.
Right. Perfect. Okay, great. Thank you.
So what, I guess, what would be considered utility in this case, like with this particular method?
So I think utility would occur if to reach utility, assuming you have, a good quantum resource, would come from being able to scale up these fragment sizes. So right now you're fragmenting these things to the point where they're easily treatable with classical resources. If you were to work with larger fragments, you would see your couple cluster results would get worse first, and then your DMRG results would start to suffer. So at some point, you would start to see advantage when you're dealing with active space sizes that, DMRG really can't treat, and a, sufficiently mature quantum algorithm could. And that's what I was trying to get at with the roughly, 150 to 200 orbital cases, because that's when we think DMRG will kind of break down for a particularly strongly correlated case.
But are you saying there are like specific type of molecules that you wouldn't be able to break down sufficiently small enough for classical computers to take, and that's why you need to handle the larger fragments?
Yeah, and that kind of goes with that strong correlation argument. So the reason the assumption behind this fragmentation is that your correlations are fairly local, which means that you don't have to include a lot of interactions between different fragments. So as your system becomes more strongly correlated, those correlation lengths get larger. And what that means is that in order to not have this truncation error arising from the embedding method, you need to work with larger and larger fragments.
Makes sense. Okay.
This is great because, actually an analog of this happens in continuous matter systems as well. And, in like disordered systems and let's say many-body localization and so on. So you have an effective length scale that is set by the kind of, let's say, physics of your model, and that tells you how easily you can fragment different regions. But then you can have regions that are order 1 but large, where order 1 doesn't mean too small, right? It could be 1,000 logical qubits. So yeah, and those, if it's strongly correlated in that region, then you cannot fragment it, and you do have to simulate that on a computer and then patch things up, hopefully. Yeah, this is great.
Awesome. I think we're at the top of the hour. Is there any last burning questions, or should we close? All right, awesome. Thank you, Luke. Thank you, everybody, for joining. Have a good day.
Thank you all.
Thanks. Bye.
Thank you.